in the last class, we had seen magnetic field due to a circular loop. So over there, we had seen how to predict the direction of the magnetic pole. We had also seen to use the Maxwell law in the other form, or Maxwell rule in the other form. Like in the Maxwell rule, we say that our thumb points always in the direction of magnetic field. So we were able to use it in the other form, that our folding fingers will point in the direction of current, then the thumb will point in the direction of magnetic field. It was the converse of it which we were using in the Maxwell law. Today we will study about a solenoid. So we will see today a solenoid. So what is a solenoid? It is a coil of many turns. It is a coil of many circular turns wound on a common core. So you have a common core, and on that common core you have concentric windings, circular windings over it, which is called as a solenoid. Okay. So just now we have seen the magnetic field due to a single circular turn. If it is a single circular turn, so we can predict the direction of the magnetic field lines from the direction of the current flowing. Now, what will happen if there is a complete coil? So we can represent a coil like this. See, a coil can be represented somewhat like this. Okay, these are the circular windings. So in this way, we can represent a circular coil. Okay. There is another way to represent this circular coil. Now, the core on which it has been wound up, it is air core. Okay, there is nothing inside it. This is called an air core solenoid. Okay, this is air core. However, you can make your solenoid something like this. You can have some other material as the core. Like you can have this material as the core, and you can perform winding over it. It can be wound over it. Like this. So this is the core. On the core, you have the winding like this. We can wind any wire, maybe something like this. Yeah. So this is also solid, but it's not air core. Within it, you have some material on which it has been wound up. Generally, we use some such materials as soft iron. We call these materials to be soft iron generally. However, we can use them as steel also, or other materials can also be used. So this is, if we use a soft iron, we will call it as iron core solenoid. Okay.
Sir, soft iron means like those which contain iron, carbon or not contain.
Soft iron means iron which do not contain carbon.
Okay,
That's a soft iron. So this is your iron core solenoid at the core. Okay. There is another way to draw a solenoid. You can have either of them, but both of them, they can be drawn in another way. There is another representation of a solenoid. It can be represented something like this. See. There are two symbols which can be used. Either you can use a cross like this, and here you can use a dot. So this is a cross dot notation. The cross means the wire is moving over here inside, and here the wire is coming in the outside. Okay. So it's like this. From here it is wound like this. Okay, it is like this. So just in this way, but this form is generally not used in your book. So you are not advised to use this one. You can use this one is your best if you use. This is the best way to draw the solenoid. Okay, as you are well aware of the windings, where the windings are going, you are aware of the directions of current. Okay, if you see this one, so in this one, it is not easy to predict the direction of, it's not easy to see where the direction is going, how it is winding. However, it's easy over here. So let's see, if I see this winding, okay, so current is moving, I take the direction of current to be like this. So let the current move like this, so that if I complete the circuit, it would be a positive terminal here, negative, positive, again negative. Okay, so this is what the circuit looks like. Okay. So in this diagram, if I want to make let me- so in this diagram, now I want to remove, I want to find out the magnetic field. So if I want the magnetic field by this first coil, what is the magnetic field inside the solenoid at this first coil, due to this first coil? Okay. So due to this first coil, if you find out, so what is the direction of the magnetic field lines? Let me mark this end to be A and this end to be B. So what is the direction of the magnetic field lines inside the coil near this first turn? Is it from A to B or is it from B to A?
A to B.
Check it out with your Maxwell rule. With the Maxwell rule, hold the current carrying conductor in your right hand, okay, so that the thumb should point in the direction of current.
Sir, is the question about the direction of the magnetic field or the direction of the current?
Direction of magnetic field. The direction of current is given. So if you observe, hold this just this much, this portion of the wire in your right hand. Okay, hold just this portion in your right hand like this. So you will observe, if you see like this, so you will observe over here that your folding fingers, they are pointing from B to A like this. In this direction they are pointing.
Yes, sir.
Okay. Similarly, if you find near this loop, it will be along the same direction, and near this loop along the same direction. Okay. So the direction of magnetic field lines, it is from B to A. If we collect all the directions, they are from B to A. Okay. So individual magnetic poles which are formed due to small circular turns, they get added up and they are along the same direction. Okay. So all the magnetic fields, they are along the same direction, hence they get added up, and therefore what you will have an overall magnetic field looking something like this. You will see that there are some magnetic field lines which are entering over here like this. They are moving out. Here you have some magnetic field lines entering over here, moving out. Okay. So in this way, you have some of the magnetic field lines. Okay. So this will be the direction of the magnetic field lines as object. So what is happening? The
Sir, it
magnetic,
will look like the magnetic barometer, right, sir?
yeah, which are exactly the same as those of the bar magnet. If you see the magnetic field line of a bar magnet, they also look like the same. They are also the same. So we find certain similarities between the magnetic field of the bar magnet and the magnetic field of a solenoid. So the magnetic field of solenoid is resembles that of bar magnet. We see here that magnetic field of solenoid solenoid resembles that of bar magnet. Hence, we say we can also, that means wherever we are using the bar magnet, at that place we can use a solenoid. Instead of using a bar magnet, we can use a solenoid, as both of them, they are forming their magnetic field lines in the same way. The magnetic field lines are same. Here also they are forming concentric circular loops like which were being formed in the bar magnet. Okay. So they are same, they are equivalent. Hence, we say that a bar magnet or a solenoid is an equivalent bar magnet. So here we can conclude a solenoid as an equivalent bar magnet. So how do we say that? This is a very important question. Everyone listen here. This question is very important. That how does a solenoid behave as a bar magnet? It's given in NCERT. It's also a PYQ in the previous years. Many number of times this question has been asked, that how does a solenoid behave as a bar magnet? Okay. So how does it behave as a bar magnet? It is because the magnetic field lines of a bar magnet, they are similar to the magnetic field lines of a solenoid. So we can say that magnetic field magnetic field lines of bar magnet resemble that of solenoid. Hence, both of them, they are equivalent. Hence, a bar magnet is an equivalent solenoid. As both of, and also you will draw both the magnetic field lines. So I'm giving you just 2 minutes. Draw the magnetic field lines of a solenoid. Draw a solenoid as I had shown over here. You can take the help of this picture. So you will not draw this one. This one you will not draw. The first one you will not draw. You will draw the second one. Okay. And draw the magnetic field lines. Okay. Draw the magnetic field lines for this second one. Everyone, draw this quickly. Draw the magnetic field lines. So Tanishka and Shreyasi, Dhruv, draw the magnetic field lines.
Yes, sir. Can you repeat, sir?
Draw, draw the magnetic field lines of the solenoid.
Okay, sir.
You can draw the wire or winding either way. Either you can draw the windings to be like this, which we used just now. So either you can draw them like this. Okay. Or you can also use them to draw like this.
Sir, is this right?
Okay, just wait, Hasmita. Wait for a minute. Let me stop sharing. Okay, Hasnita, you can show. Mm, okay. Also make the direction of current. And the direction of magnetic field lines is not correct. Okay, if you check the direction of the magnetic field lines, it's not correct. They are opposite.
Okay, sir.
Okay, okay, check it. First draw the direction of current and then draw the magnetic field lines.
Yes.
Okay. And who else has drawn? Mehak, have you drawn?
Yes, sir. Just 1 minute. Sir, can you check mine, please?
Just wait. Yes, that's correct. Now you need to complete the magnetic field lines. Complete the magnetic field lines as we complete in the case of bar band.
Okay, sir.
Your direction is correct.
Sir,
Yes.
sir, I did it without the magnetic field lines. Should I do it after?
You didn't do.
Magnetic field lines I did not do, sir. I'll just do it and show it to you.
Show it how much you have done. Magnetic fields. Okay, so complete it. Complete the field lines. Okay, man. Rene. Rene.
Sir, can I show,
Yes,
sir?
Okay, Shreyasi. You saw. Hasnita, your camera is also off.
Yes, sir, I'm making.
Uh, so better. That's why I told you not to make this one. Okay, you should not make this one as solenoid. You yourself will be confused. What is the direction of winding? If you look from one side, it will look that it's folding like this. If you look from the other side, it will show something else.
Sir, that is why, sir, I put A and B, sir, on the corners.
Show it once more. I don't think that it's okay. No. It won't work. Okay, it can be considered one. See, it can be considered it's good, but if you want to score full on full, then it's not correct.
So, sir, when I'm making such type of, sir, like I have to put the iron core in that, sir.
Yeah, that would give a better look.
Then
So
how
there,
are we supposed to represent from which side to which side the coil is? How will it be understandable, sir?
you can take either side, then the direction of current is already understood in that. You
Hi,
need
sir.
not put A and B. Try to do the best. It's good. Okay. Till you are scoring 98, it's good. But if you want to score 100, then it's not good. Medha Hansini, Rene, just show your diagrams. Okay, Rene. Rene, direction of magnetic field lines. See, you have drawn those small field lines. They are correct. You have got them correct. But the big ones which you have made, their direction is opposite to those small ones. Check it, Rene. Or just show it once. I will show you. Okay, see here. See, these small magnetic field lines you have made correctly. Got it, Rene?
Yes, sir.
Yeah, correct them. So in this way, you can make these small magnets. These small magnets which are made, they are called as temporary magnets. Okay. In this way, the iron core which is placed inside it is magnetized. The iron core which is placed inside that also gets magnetized, as iron is a magnetic material. If you instead of iron you put other materials like bismuth, copper, they do not get magnetized. Okay, your steel, iron, nichrome, they get magnetized. Alnico, which is an alloy, it also gets magnetized. They are used for making permanent magnets. So I hope everyone has shown. Whoever has not shown, I think they would have corrected them. They might have corrected them. I expect that they have corrected by looking at all the others. Okay, if they were wrong, so they would have got corrected it. Okay. If you feel that you have any doubt, you might be wrong, you might be incorrect. So you can share it later and we'll check it. Okay. See. Now, what we wanted over here, that this substance which is put inside it, it becomes a temporary magnet. It is a temporary magnet, and such temporary magnets, they are called as electromagnets, as they are made with the help of electric current, and their magnetism lasts only till there is an electric current. If there is no electric current, so there will not be any magnetism in them. They will lose their magnetism. Okay. However, this is also the method of making permanent magnets. Even if you want to make the permanent magnets, so this is the same method by which you are going to make the permanent magnet. Okay. So the question may be asked that you may be asked to list out the similarities between a solenoid and a bar magnet. These are the two important questions from it. You can be given similarity between a bar magnet and a solenoid. So similarity between a bar magnet and solenoid, or you can also be given differences between them. So what are the differences between them?
Sir, the bar magnet can permanently have the magnetic field line, sir, but the solenoid can only have the magnetic field line when there's a current, sir, and it depends on how much current we give, sir.
Yeah, a solenoid can have a magnetism only till there is current. Okay. Any other difference? Any other difference? Mehak, any other difference between solenoid and a bar magnet? Monish? Monish,
Yes, sir.
what's the difference between a bar magnet and a solenoid?
I'm not sure, sir. I'm just thinking about the point.
Hmm.
Sir, solenoid can be air core, right? Like,
Okay, it can be iron core or air core. But what is the difference that we see here? First of all, the solenoid is a temporary magnet. Okay. And it is a temporary magnet. You can increase or decrease its strength. You can make this to be a strong magnet or you can make it a weak magnet. So increase or decrease the strength of magnet.
Sir,
So we
magnetic.
can reverse.
Yeah.
Sir, can it be magnetic force?
Magnetic force. No, it cannot be magnetic force. If there is magnetic force, so both will act the same way. Both are going to give you the magnetic forces.
So we can reverse the current in
Yeah.
solenoid, and we cannot do that in bar magnet.
So you can change the poles of magnet. Poles can be changed. In temporary magnets or in solenoid, you can change the poles. You can change the polarity. Like if this is the north pole, this is the south pole, so you can reverse. You can make this to be the north and this to be the south by changing the direction of current. If you change the direction of current, so the polarity will change. Okay, so these are certain differences between bar magnets and solenoid. We also saw the similarities between the bar magnet and solenoid, that both of them, they are almost similar. They produce similar magnetic field lines. Okay. Now we'll see. So everyone has understood up to here.
Yes.
Okay, so our new concept is force experienced by a current carrying conductor in a magnetic field. So if you have somewhere a magnetic field, and in that magnetic field, you place a current carrying conductor perpendicular to it. So this is also an important point. The current carrying conductor should be placed perpendicular to the direction of magnetic field. If it is parallel to the direction of magnetic field, so there will not be any force experienced. So various examples and activities are given. Like one, you will find one activity has been done with the help of mercury. Okay. In your NCRT, you will find an experiment which is done by using a bar magnet. So we take here an example of bar magnet. And using this bar magnet, we draw, let this be the bar magnet. So this is our bar magnet. And let's say this to be the North Pole and South Pole. between the poles of these bar magnets, we hang a metallic conductor. So let's put here a metallic conductor which is placed between these. Okay. This is a metallic conductor which may be your metal scale. You can take your metal scale also. Okay. And okay. So now we make your two wires. We just make it in contact with the two wires. And the two wires, they are wound on like this. Okay. So this is an insulating stand. Okay. This is just the stand. And these two wires, they are connected like this. They are connected on this with the battery. So they are connected with key and battery. It's like this. Just so this is just a simple experiment which demonstrates the force acting on a current carrying conductor. So as we see that there is a current carrying conductor, a scale, which is held between the poles of a magnet. Okay. Now the magnetic field lines, they are passing perpendicular to this. Okay. The magnetic field lines from this bar magnet, they are passing perpendicular to this. The magnetic field lines are passing like this. Now, if we turn on the switch, if you turn on the switch, so what will happen? Current will start flowing through this wire in this direction. This will be the direction of current. So current will start flowing, and because of which this scale or this conductor, it will show deflection from its original position. It will get deflected to one side. It will move to one side. And this will happen only when the current is switched on. If the current is switched on, so you will see this. If the current is off, you will not see this effect. Okay. So what happens? The scale experiences a force because of which it moves out. It rotates and moves out. Okay. So with this activity, we are just able to demonstrate that a current carrying conductor experiences a force when it is placed in a magnetic field. So the factors on which this force experience depends. Now the key points. First one, conductor experiences a force conductor experiences force when there is current in the coil. So there should be current in this conductor. Okay, when there is current in conductor and when conductor is perpendicular to magnetic field, both the points should be there, perpendicular to field. If you place the conductor parallel to the field, there will not be any force experienced. If you place the conductor something like this along the north-south, So it would not experience any force. So now see the amount of force, it depends on the strength of the magnetic field. Amount of force, it also depends on, so here the force, it depends on magnetic field, that is how strong the magnet you are putting, and it depends on the amount of current that is flowing. So it depends on the amount of current that is flowing. And magnetic field, also it depends on angle between conductor and magnetic field. So these are some of the important points which you will not find listed anywhere. They are not listed anywhere in your book, but just go through this. Just see this complete activity. What are the important points over here? That there will be a force experienced by a conductor. Now this force, how it is experienced, we will see the direction of the force. Okay, so shall we move ahead now? Here, actually, the force is being experienced by the charges which are there. Now, force is a vector quantity. See, we have force as also a vector quantity. We have magnetic field, which is also a vector quantity. And we have direction of motion of conductor. So motion, that is also a direction, and hence it is also a vector quantity. So how do we determine that in which direction will it experience the force? Why the scale or why the conductor will move all along this direction? Why it will move clockwise? Why it will move anti-clockwise? So all these reasons, they are explained over here in the Fleming's rule. Okay. So this is your Fleming left hand rule. Okay. This is your Fleming left hand rule. So what is this Fleming left? Yeah. Anyone can state Fleming left hand rule? Is there anyone who can state this?
Sir, is it the index finger, middle finger, and the thumb stretched out to be perpendicular?
Yeah. Yeah. Complete the statement.
They all are mutually perpendicular to each other.
Stretch the forefinger, middle finger, and the thumb of your left hand mutually perpendicular to each other. Right? Then what will happen? What are the
So
directions?
the middle finger will be the motion.
Middle finger will be motion.
Middle finger will be direction of magnetic field. Index finger will be direction of electric current, and then the thumb will be the direction of deflection of the conductor.
Okay, so stretch your middle finger, these three fingers of your left hand, your thumb, Your this was thumb, forefinger, and the middle finger. Okay. So how we remember this? What happens? I'm writing here. You will remember force is experience. Force experience, it is given by your thumb. Then electric field, it is given by your forefinger. And middle finger gives you the direction of current. Middle finger, it gives you the direction of current, not motion. Motion is in the direction of force. Okay. So the third one is your current. The direction of current is given by your middle finger. Okay. So how to remember this? Out of your three fingers, which is the finger that's most important to you for working everything? You can't work anything without that finger. You can't write with that without that finger. You can't do any other job without that finger.
Sir, all three, sir.
Yeah,
Sir, all three, sir.
all fingers. Okay.
The thumb is the most important.
Out of them, your thumb is the most important. If you are going to hold a spoon, you are going to hold anything, so you don't hold with these two fingers. You take the help of your thumb. Okay. So whenever you are applying a force, then your thumb is important. You also have heard that story of Eklavya, where he donated his thumb. Okay. So your thumb is considered as a sign of force. So in this way, you can remember that since thumb represents the force, therefore here also your thumb will represent the force. Okay. Then your middle finger, it's also called as central finger or center finger, right? So C for center and C for current. And the remaining is forefinger, F for forefinger and F for feet. Okay. So in this way, you can remember all of them.
Sir, then instead of force, we can add motion also, right, sir? Or else we'll get confusion between force and field. Which one F should we take, sir?
Yeah, you can take this to be a motion. The direction of motion or the direction of force. That will be given by your thumb. Okay, so see, to find out the direction of force experienced by a conductor, you must stretch your thumb, forefinger, and the middle finger of your left hand. This is also important, and most of the time we use our right hand. Okay. So by mistake, whenever you will be finding, maybe sometimes you need to check it out once more that whether you are stretching your left hand or your right hand. Okay. So in your left hand, all the three fingers, they should be mutually perpendicular to each other. If the three fingers, they are mutually perpendicular to each other, so what will happen in that case? Try to arrange first one finger. Okay. Out of the given two quantities, let us say sometimes you might know field and current. If you know the direction of field and current, so arrange your first current and then arrange the field. Suppose if you know the direction of current, so you just need to rotate your hand like this to have the direction of the magnetic field line. It will always be perpendicular to it. So just rotate your hand in this way so that your direction of current remain the same. Keeping that direction same, and then you can find out the direction. Okay. I think many of you find problems in rotating your hand to find out the direction. Sometimes you do like this and sometimes you do like this. So just keep in mind, keep your one of the finger. First arrange one finger, okay, and let that be central finger. Okay, arrange this in the direction of current. Then just rotate your hand, keeping one of the directions to be the same, keeping your current to be the same. If the second one is also arranged, you will get the direction of the third one. So I'm completing just this statement, then I'll give you one of the questions. Okay. So stretch the forefinger, middle finger and thumb of your left hand mutually perpendicular to each other. Then if the center finger point in the direction of if the center finger point in the direction of current and forefinger point in the direction of magnetic field, then the thumb point, another point I will tell you about this, then the thumb points in the direction of magnetic field lines. Okay, in the direction of force experienced, not magnetic.
Yes,
In
sir.
the
For
direction of force experienced. Okay. Okay, so this is the complete statement for this. Okay. So stretch the forefinger, middle finger, and thumb of your left hand mutually perpendicular to each other. Then, if the center finger point in the direction of current and forefinger point in the direction of magnetic field line, then the thumb point in the direction of force experienced by the conductor. Okay. So let's try to solve a question out of it. Okay. Okay, just see this question. Example. So an electron enters a magnetic field at right angles to it. As shown in figure 13.3, the direction of force acting on the electron will be. What will be the direction of force acting on it? Let me give you the diagram also. So use your left hand rule. See, we take just remember, we take the direction of current to be the direction opposite to the direction of motion of electrons. Okay. In the circuit, the direction of current is taken as opposite to the direction of current, the direction of electrons. So here, if the electrons are moving in like this in the downward direction, so the direction of current that we will take, it will be along this direction. This will be the direction of current. So come on, tell me, in which direction will there be a force experienced? This is your current, this is your magnetic field.
Sir, to the left.
No, it's not left. It will be perpendicular to both of them. And if you see perpendicular to both of them, it will be either out of the board or it will be into the board. These are the two directions which are possible. With your left hand, just if you do your current like this, and then rotate your hand so that like this. Just rotate your hand. Now you will find. Keeping this direction of current to be the same. Okay, keep the direction of current to be the same. You rotate your hand, and once your fingers are arranged in the direction of magnetic field line, then you will find that it will experience a force in the inward direction. The electrons will experience a force into the plane of paper.
So, sir, it is into the page, sir.
Yeah, it's into the page. Okay, Rene, is it clear to you?
Yes, sir.
Okay. Now let's see
Sir,
the
I'm
next
kind
one.
of not understanding this concept, sir.
You are not understanding this concept. Okay, first of all, you got the direction of current. Why we took the direction of current in the upward direction?
Yes, sir, that I understood. Sir.
Okay. So arrange just your one middle finger in the direction of current. Middle finger. And rotate your hand. Just rotate your hand, keeping this to be fixed. Keeping your middle finger fixed. Rotate it so that your forefinger starts pointing in the direction of magnetic field line. Rotate it like this. Rotate and see your this forefinger should point in the direction of magnetic field.
Yes, sir, understood. Sir.
Understood?
Yes, yes.
Sir, are you able to get?
Yes, sir.
Okay. Manan?
Yes, sir, I got it.
Okay. So will you do another question?
Yes, sir.
Okay. See, this question is also very conceptual question. Okay. Remember, I'll be if you can do this question and explain it to me in the next class, it will be very good. I'm giving it to you as homework. It will be available in the PDF file. Okay. So it's available over here. You can do it, solve it. Okay. This is a conceptual one, not on the directions. This one is based on the direction. The question 3 is based on the directions. Okay. So just do this question 3. I will help you out. Do this. See, here there are no electrons. These are positive charges. Okay. And the direction of positive charges is the same as the direction of magnetic field lines. Okay, so again they are talking of north, south, east, west. So you will make your directions. So your directions are like this. Okay. So this is your north, south, east, west, and you have your upward and downward. This one is upward, this one is downward. Okay. So let's try to make what the question says. Positively charged alpha particles projected toward west. So they are projected toward west. So of course they are moving from east. So this is the direction of current, right? The direction of current I. is deflected towards north. So they are deflected towards north. So towards north in this direction, this is the direction of force experienced. Your force experienced is towards north. You have to find out the direction of magnetic field. The direction of magnetic field is. So again here, arrange one of the fingers and then rotate the other, keeping it fixed. Like here, I have the direction of current over here. So I keep it as fixed. Then I keep my thumb in the direction of force. As per my diagram, I experience that my forefinger is pointing in the upward direction. And you should also check out if you are getting the same thing or is there anything different. Yes, all of you are getting your this forefinger in the upward direction.
Yes, sir.
Okay. So I hope all of you, is there anyone who cannot apply these directions? So this is a direction of magnetic, sorry, we have to find the direction of this thumb, right? Not a thumb is given. That's correct.
Correct
We have to
only, sir.
find field only. So it will be your upward direction. This is your magnetic field B. Okay. So it's upward. Okay. So bye everyone. All of you may
Sir, I
leave.
have a doubt, sir.
Yes.
In the Sunday's test papers, sir.
Okay. What was doubt?
Sir, it asks, sir, the main function of cerebrum is thinking, hearing, memory, or balancing.
Balancing. Body
Sir,
posture
why
is
not,
also.
sir?
So,
Yeah.
but then that's the cerebellum, right, sir?
Yeah,
Balancing.
that's the
Okay.
cerebellum. Right?
Cerebrum. Okay. Okay. It's cerebrum.
Cerebrum is thinking, right?
Cerebrum is thinking.
Sir, I think you should change the answer in test, sir.
Yes, sir.
Okay. Was it cerebellum? Was
Yeah,
it?
okay, they said main function of cerebrum and it was marked as balancing.
Okay.
Yeah.
Fine. Okay. Okay. I'll check it out.
Yes.
Okay. Okay. Fine. Bye
Sir,
everyone.
sir, can you explain one more question, sir?
Okay. Which one?
It was the second question. Sir, it asks, a constant current flows in a horizontal wire in the plane of the paper from east to west. The direction of the magnetic field at the point will be north to south.
So where will it be north to south? Will it be up above the wire or will it be down the wire? Below the wire?
That's why I'm getting confusion, sir.
Okay. So just let me share again. So, okay, so you have the direction of current. What is the direction of current they are giving?
So the current is given from in a horizontal wire from east to west.
East to west. Okay, let's make the directions also. So this is your east, west, north, south. This is the direction of current. Okay.
Yes, sir.
So if you observe the magnetic field lines as per the Maxwell rule, they will be like this. So above the wire, if you see above the wire, the magnetic field lines will move from south to north, and below the wire, they will move from north to south.
North to south. So, sir, north to south means it goes below the wire.
Yeah, north to south means below the wire. It was the question that we had discussed, but in the opposite way.
Okay, fine. Sir. Yes, sir.
Okay, bye everyone.
Thank you, sir. Bye.
Okay, bye.